In this lecture, we're going to try and advance some of the concepts that we had in lecture 14, where we started to talk about compression, and we just sort of saw the tip of the iceberg with regards to efficiency. So both of the example problems that we're going to work through today deal explicitly with efficiency. And so here, let me bring up what we're going to be working on. So the first example problem says that saturated steam is compressed adiabatically. It enters the compressor saturated at 100 kilopascals and leaves at 300 kilopascals. How much work is required, and what is the final temperature if the compressor efficiency is 0.75? Okay. Now, in the last lecture, I said that we're going to do something every single time that we have a compressor problem. And what was that?
We have to solve for the isentropic case.
That's right. Every single time we have a compressor or a turbine problem, we're going to solve for the case where the process is at 100% efficiency. And then we're going to use that information either if we know the efficiency to find the final state, and that's what we're doing here. And other times we'll know the final state and we'll be asked to find what the efficiency is. Okay. And so we know that, when we have an isentropic system and we have this compressor, right, it's basically reversible and adiabatic, right? So here we're going to find where delta S of our system is equal to 0. All right, so we're going to do that in both this example problem and in the next one. So let's do that here. And in the isentropic case, the things that we are normally going to be after are very similar to what you're asked in the problem. So you're almost always, for the isentropic case, we're going to find, right, for this compressor problem where we know the initial temperature and we know the pressures. And I know you might say, oh, well, we don't actually know the initial temperature, but we do, because we know that it enters the compressor saturated at 100 kilopascals, right? So we'll be able to use the saturated steam tables for that. And then when we get to 300 kilopascals, it'll be hotter, so we'll have superheated steam. So we need the final temperature. And then we're also, if we're interested in work and efficiency, right, we're gonna have to find delta H. And so those are really the two parameters for compressor problems that we're almost always gonna solve for, because you essentially always know the inlet temperature, and then you'll know the final pressure, because we compress to a pressure that we're interested in, either for flow reasons or because we want a reaction to happen at a certain temperature. Okay, so we know we're gonna have to find this. We're gonna have to find T final and delta H when delta S is equal to 0. But where this is a little bit different than what we did in the last lecture was that before we used oxygen, right, which was, you could assume, at least initially, was a simple ideal gas. And then even when we relaxed the simple assumption, right, you still could assume it was an ideal gas. And when that was the case, right, we used the relation for the heat capacity that's in the back of your book. Well, here we're using saturated steam. So if we're using steam, what tool are we going to use to solve this problem?
Steam table.
Yeah, we're going to use the steam tables. And doing so is, can be involved. So we're going to need to get values from the steam tables, and we're also going to have to use that interpolation formula that I talked about last time and that I demonstrated as well. So we know that steam is going to enter the compressor saturated at 100 kilopascals. And if you go to the saturated steam tables at 100 kilopascals and at its saturated condition, which is, by the way, 99.63 degrees C, we know the value for the entropy. So we can read from the steam tables that the entropy is equal to 7.3598. And actually, I'm not going to write this little S1. And we know that the enthalpy at that state is equal to 2675.4 kilojoules per kilogram Kelvin. Okay, so if we're going to solve this isentropic case, then delta S is equal to 0 then for the isentropic case. So for this isentropic case, S final is equal to S initial, which is equal to 7.3598, right? And the units for that, I didn't write that above, are kilojoules per kilogram Kelvin, okay? So our task then is that we know the final pressure is 300 kilopascals, and we know what the final entropy needs to be. So what we need to do is to look at the steam tables for what temperatures have values that at that pressure that are very close to 7.3598 kilojoules per kilogram Kelvin. So if you go in the steam tables and look for a few of those values, so at 300 kPa and 200 degrees C, that the entropy there is equal to 7.3119, and the enthalpy there is 2865.5, right, with the same units above. And then at 225 degrees C, the entropy value is 7.4177, and the enthalpy value is 2916.9 kilojoules per kilogram Kelvin. So this is good. We found two entropy values in the steam tables at the exit pressure that surround what we know for the isentropic case is the final entropy. So what we need to do to find the actual final temperature and the final enthalpy is to use the interpolation formula that we used last time. And remember that that formula in the steam tables, right, it's like the first page of the steam tables, is M is equal to x2 minus x over x2 minus x1 times M1 plus x minus x1 over x2 minus x1 times M2. And in this case, the M is the thing that we're after, or maybe in every case, M is the thing that we're after. And in this case, M is the temperature, right? At least that's the thing that we'll solve for first. And then the X's here are the entropies. And in this formula, the entropy that you know, right? The X's are the things that you know, is the final entropy value. That X2 is the entropy value at the second state. And I always use that as the higher temperature. So we know that that's X2. And then X1 is going to be the temperature in the other state, or just by convention, I always use the lower temperature as 1 and the higher temperature as 2. So let's apply then this equation to the data that we have. So we then know that our final temperature should be equal to X2, which is the entropy at 225 degrees C. So that's 7.4177 minus our target entropy, which is 7.3598, divided by 7.4177 minus 7.3119 times, then M1 is the lower temperature. So that's at 200 degrees C, then plus X, which is our target value, 7.3598, minus the lower value, which is 7.3119, divided by then X2 minus X1 again, times M2, which is the higher temperature, which is 225 degrees C. And if you solve that, you'll find that the final temperature for the isentropic case is equal to 211 degrees C. All right, before I move on at all, does anybody have any questions about that?
So it doesn't matter that it's in Celsius and not Kelvin?
No, because the only thing that the interpolation formula does is it draws a line. It's just drawing a linear line between the data points. So the scale doesn't matter in that case. You would just shift it around. You could use Kelvin if you wanted, but you would get the exact same answer because that's all it's doing. It's just drawing. This is like the formula for a straight line. It looks a little bit more complicated than that, but it's not. Okay, good question. All right, any other questions? All right, if not, let's move ahead to the enthalpy, right? Because we're asked for the final temperature and we're asked about how much work is required. So the amount of work, remember that that's just m dot delta H from our energy balance in the last lecture. So let's find the enthalpy. And if we're going to do that, well, we're just going to solve this exact same interpolation equation again, right? Except this time, m is going to be equal to the enthalpy values. And again, x is going to be equal to s. And so if we apply that, well, then this just becomes the enthalpy of the final state is equal to the same things in parentheses, right? Because the x values didn't change. 7.4117 minus 7.3598 divided by 7.4117 minus 7.3119. But now we're going to use the enthalpy value at the lower temperature, right? Because M1 is this value, right? So that's then times 2865.5, then plus that stuff in parentheses up there again, 7.3598 minus 7.3119 divided by 7.4177 minus 7.3119 times the enthalpy at the higher state that we pulled from the steam tables, right, that I just circled in magenta. So that's equal to 2916.9. And we can find that the enthalpy in the final state then is 2888.8 kilojoules per kilogram. Okay. And then from there, we know we need to calculate work. So let's calculate delta H. Well, of course, delta H is just the final state minus the initial state. So that's 2888.8 kilojoules per kilogram minus our initial value, which was 2675.4, or delta H is equal to, and that's delta H, to be a little bit more specific about it, when delta S is equal to 0, right? This is the isentropic case. That's equal to 213.4 kilojoules per kilogram. And so the very first thing in every problem for a compressor, solve the isentropic case. And that's what we've done. So now we have the final temperature and we have the final enthalpy when delta S is equal to 0. And so we can use this to find the real work that you have to do and to find the real final temperature. And the way we're going to do that is that if you remember that the efficiency for a compressor is equal to delta H when delta S is equal to 0 divided by delta H, and we called this delta H real in the last lecture. So delta H real, or the non-isentropic case, is just equal then to delta H for the isentropic case divided by the compressor efficiency. And if we do that in this case, well then delta H real equals then 213.4 kilojoules per kilogram divided by the efficiency, which we're told in the problem is 0.75. And so delta H real is then equal to 284.5 kilojoules per kilogram. All right, so this is the, when we're asked about how much work is required, well, there's that, right? There's the amount of work that's required. So how are we going to use this new information about delta H to find the final temperature? The real final temperature.
We go backwards, so we just plug it back into our equation. So we add, or we set the equation delta S equals 0 equal to 284.5 and solve for our new H final, and then from H final we can find T final.
Yeah, I conceptually you've almost got it there, right? You are right that we're going to work backwards in the sense that, you know, before, right, we were finding the temperature and enthalpy from our entropy value where delta S was equal to 0. Well, in that case, the entropy was the thing that we knew, right? So, you know, the entropy was the X's, the temperature and enthalpy were the M's, right? In this case, now if you think about it, we actually know the enthalpy and the final state, because, you know, delta H real is just equal the enthalpy at state 2 minus the initial enthalpy. And I didn't use 1 and 2 before. I kind of used final and initial, so I'll keep that here. So we know that the final enthalpy, right, is equal to delta H real plus the enthalpy of the initial state. And we have the enthalpy of the initial state above here. So we knew that it was 2675.4. So that's 2675.4 kilojoules per kilogram plus the real delta H, which we just calculated as 284.5, right, kilojoules per kilogram. So the final enthalpy for our real process is then just the sum of those two numbers, which is equal to 2959.9 kilojoules per kilogram. And you're right. So now we're going to sort of work backwards in the sense that now we're going to use the enthalpy to find the temperature, right? And that equation, again, right, was that M was equal to x2 minus x over x2 minus x1 times M1 plus x minus x1 over x2 minus x1 times M2. And now, in this process, M is equal to the temperature, and the x's are the enthalpies that we know. And now this is going to be our target enthalpy. So I went in the steam tables, and we're still at 300 kilopascals because the pressure is the same. So now what I'm looking for are consecutive data points in the steam tables, one that has an enthalpy value just above this one, underlined in red. So one just below and one just above. And if you do this, then at 300 kilopascals, at 225 degrees C, that the enthalpy value is 2916.9 kilojoules per kilogram. And at 250 degrees C, the enthalpy value is 2967.9 kilojoules per kilogram. And obviously, right, this one is just a little bit above our calculated value, and this one is below. So we should be able to use this exact formula to find the final temperature. So if that were the case, right, so there's T final is equal to, so X2 is the enthalpy at sort of state 2, and so I'm going to use this as state 2, and I'm going to use this to give me the ones. So that means that T final is X2, which is the enthalpy of this state 2 from the steam tables, which is 2967.9, minus the targeted value, which is 2959.9 kilojoules per kilogram, over 2967.9 minus 2916.9. 0.9 times the temperature 1, which is 225 degrees C, plus then 2959.9 minus x1, which is 2916.9, divided by 2967.9 minus 2916.9 times T2, which is 250 degrees C. And so the final temperature then leaving is 246.1 degrees C, which is actually quite a bit higher than the initial temperature or the isentropic case, right, where we calculated that that value was 211 degrees. So it's about 35 degrees C hotter than the isentropic case. But here, we were able to find both the final temperature and the work that was being done by this particular compressor. And we started it by solving the isentropic case, where we solve for the final temperature and enthalpy that were leaving the system if delta S was equal to 0. Then we used the final enthalpy to calculate delta H, and then delta H divided by the efficiency was the real work that was done. And then we used that delta H to find the final temperature from the steam tables. Does that flow make sense to you guys? Do you have any questions about anything that I did here or something that might be confusing?
I think it makes sense. I also think another problem will help it be a little clearer.
Yeah, and this is something that, first of all, I will encourage you guys actually to solve this problem on your own, because you have the answer and you can just make sure that you can go through the method. Homework 5 will also have a bunch of compressor and turbine problems as well. So after the exam, you guys will definitely get to practice this a little bit more. And hopefully that helps. And if not, obviously, we'll work through it during office hours as well. So good. Now, actually, speaking of exams, I do like to point out when I do this, just so you guys can get a sense for my style. So in 2018, our second example problem was an exam problem. And we're going to follow a very similar methodology to what we did just a moment ago, except in this case, we're going to calculate the work that was needed to compress 50 kilograms per hour of CO2 instead of steam. And we're told it doesn't behave as a simple diatomic ideal gas. Well, it really should be simple triatomic ideal gas, because obviously CO2 is never going to be a diatomic gas. But hopefully you know what I mean here. From 200 degrees C and 5 bar to 25 bar, if the compressor efficiency is 78%. And then how much current would the compressor draw if the operating voltage were 220 volts? And here we're going to use really the same result that we used above, that first we have to solve for the isentropic case, and then we're going to, from the isentropic case, find the real amount of work that needs to be done. And if you remember, our energy balance for a compressor simplified to the work is just equal to m dot delta H, right? And then we had equations for the efficiency being equal, either to the work for the isentropic case over the real work, or, we also said that the efficiency could be, that's the same thing as saying it's delta H for the isentropic case, divided by delta H real. All right. And that means our primary objective is to still determine the final temperature and enthalpy. Now, when you use the steam tables, you have to do interpolation. So the methodology there is sort of unique to steam. But for all of these other gases, the methodology follows the equation that we derived a couple of lectures ago, where for the isentropic case, we know that the change in the entropy over R for our process is equal to the integral from T1 to T2 of Cp over R dt over T minus the natural log of P2 over P1. And if we're not working with steam, right, we're working with another gas, we're going to use this equation, because if you set that equal to 0 for the isentropic case, well, we have the initial temperature and pressure, and we have the final pressure. So the only unknown in this equation is the second temperature. And the complicating factor here is that the heat capacity is not for a simple triatomic ideal gas. So we know in this case, Cp over R is not equal to 9/2, which it would be if you were allowed to make that assumption. In this case, we know instead that Cp over R is equal to the equation in the back of your book, where that's the polynomial, right? A plus B times T plus Ct squared plus D divided by T squared. And I missed a C, didn't I? Sorry about that. That's Ct squared plus D over T squared. I said it, I didn't write it. And we can get these parameters for CO2, and we know that A is equal to 5.457. We know that B is equal to 1.045 times 10 to the minus 3. C is equal to 0, and D is equal to minus 1.157 times 10 to the 5th. And so if we plug this into our integral, right, so 0 is equal to, right, the integral from T1 to T2 of Cp over R. So this just becomes, you know, A over T plus B plus, and we know C is equal to 0. So that's not, we don't have to take that into consideration anymore. D over T cubed dt minus the natural log of P2 over P1. So then 0 equals A times the natural log of T2 over T1 plus B times T2 minus T1 minus D over 2 times 1 over T2 squared minus 1 over T1 squared minus the natural log of P2 over P1. And again, we know T1, right? So that's 200 degrees C, or 473.15 Kelvin. We know that P2 over P1 is equal to 5, right? Because P2 is 25 bar, P1 is 5 bar. And so we can solve this equation. I did it in Excel just using GoalSeek and found that T2 was equal to 629.5 Kelvin, right? Or, you know, 356.4 degrees C. And the reason that is helpful is because now we can calculate delta H, right? Because delta H is still equal to the integral of Cp dt from T1 to T2. And since we have Cp over R, then delta H is just R times the integral from T1 to T2 of Cp over R dt. And that's equal to R times the integral of A plus BT plus CT squared plus D over T squared dt. And again, you know, C is equal to 0, so we won't bother with that moving forward. So then delta H just equals R times A times T2 minus T1 plus B over 2 times T2 squared minus T1 squared minus D times 1 over T2 minus 1 over T1, right? And so we have T2 already when delta S is equal to 0, and that's 629.5, and we have the initial temperature. So then delta H for the isentropic case is then just equal to 7340 joules per mole. And so we can calculate then the work when delta S is equal to 0, right? Which was just equal to m dot delta H. And that's equal to 30 kilograms per hour times 7340 joules per mole. And then we can just do a little bit of correction for this kilograms
Dr.
and
Miskine,
moles. Yeah.
Isn't it 50 kilograms per hour in the problem statement? Or is that from something else?
Oh, I'm sorry. Nope. I tried to just remember it and I was wrong. You're totally right. It's 50 times 1,000 grams per kilogram. So thank you for that. Times 1 mole of CO2 is about 44 grams. And then we know that you have 1 hour is 3,600 seconds, right? And this makes sure that we're going to get the answer in the right units. And so that equals 2,316 joules per second, right? Or watts, right? And so then this is the isentropic work. So the real work then is just equal to the isentropic work divided by the compressor efficiency, right? So this is 2,316 divided by 0.78. And that is equal to 2,970 watts. And that's the real work that's being done by this compressor, right? 2,970 watts. And the last question is how much current would the compressor draw if the operating voltage were 220 volts? And of course, we know from what we've done before that the power, right, or the work here is equal to the current times the voltage, right? So current is then equal to power over voltage, which of course is 2,970 watts divided by 220 volts, and a watt over a volt is an amp. So that's 13.5 amps.